Okay, I'm just going to introduce Cartesian coordinates. In 3D computer graphics, we use a Cartesian coordinate system. In this system, we have an origin and three direction vectors called x, which is here, the blue pencil, pointing to the right of the screen, y, pointing to the top of the screen, the green pencil. It's positive x, positive y, and positive z, pointing in relation to us out of the screen towards you. So that's the yellow pencil here. That is negative z, negative x, and down would be negative y. So we can do quite a lot with these coordinates. So I'll just bring up a planar, and basically this is a 2D shape within the 3D environment in Maya. Okay. So what I will do is I'm going to create a proper cube, and they're going to be 1 unit. Each side will be 1 unit. So we have the scale in terms of the x, which is to the right, and that's 1 unit. Y, 1 unit up, and 1 unit out. So we have our cube. We can translate it to any point. I've set the pivot to 0, 0, 0, 0, which is the bottom or the back left point on this cube. So I'm going to translate this 2 in the x, let's say, minus 2 in the y, and 3 in the z. You can see now it's dipped below our grid, and that's because it's dropped by minus 2 in the y, and it's in terms of the z-axis going across here, and if we were, this is essentially pointing out towards us, remember, so it's going out in the z, and it's to the right of the origin, which is 0, 0, 0, and it's 2 points to that. 2 points in terms of the x. Okay, that's an example of what we can do in terms of the translate. We can also move individual parts, and in terms of the vertex here, if we want to take this particular vertex and move it, if I press that, I hold down X, we can move it 1 point in the X, maybe 1 point in the Y, and hold down X, and 1 point in the Z. Okay, so that should be 2 points there. Okay, so as you can see, it really can describe in terms of these Cartesian coordinates. If I was to take, so if I go back to object mode, obviously the origin is the same. What we have now, we can manipulate this shape and give it a very original character, or shape it into any sort of object we like. And these coordinates can really assist in that. Okay, so in this part I'm just going to show you how I've added and subtracted vectors. So we have vector A and vector B, and basically what we are going to do is, first of all, if you walk along here, this is the tail and this is the head. This is the tail and this is the head. As you can see, they have different directions, quite different direction, and different magnitudes. We can basically add these together by, if we wanted to add A to B, we would walk along B to get to the head, and then starting at the tail, we would add A, and wherever that ends up will give us our end point for a new vector. So if we do that, as you can see here, that's essentially taking this line, which is the vector A, adding it to B, and it ends up being here. From that point, we can then actually create a new vector, which we will call D, and we can then get rid of A, and that's essentially what we get with D. So the point of that is -4, 3 in the y-axis, and 9 in the z-axis. So we can check if that's correct by using the script editor. And so here we have A and B, and if we run that, that's going to inject the coordinates into the script editor, and then we can run both of these. Okay, it's going to give us each of the points. So the result of that is 7, 8, 7, and the result of A is -6, -5, and 9, and essentially you can then run D, and D will give us so. But to then get the exact position of D, we can run this code here, which will give us the exact coordinates of D. And there we have -4, 3, and 9. So next we can take a look at, for instance, adding B to A. Okay, so if we walk along A and then add B, that will give us this point here. See? Okay, and then essentially starting from the tail of A, we can join that up to the head of this additional, the B that has just been added to the head of A, and that'll give us point E. We can then get rid of B, and this is our new vector. So if we just click on that, that will give us 8, 9, and 16. We then can get up our script editor, and we have obviously run both of these. But we can now run E, so that'll give us that, and this, and then to get the exact coordinates, we run this bit of code here, and the result is 8, 9, and 16. Okay, so that is addition, the addition, so to add two vectors together. And what we can see from that is that if we take the result of both of these, they're identical. So their magnitude and direction are identical. As you can see here, so if I was to just get rid of B and A, you can see here that the direction and magnitude of both D and E, so that means when we add A to B or B to A, the resulting vector is identical. Okay, so now I'm just going to show you an example of the subtraction of two vectors. So I've created another vector here, C. We've already used B. So what I'm going to do is I am going to subtract B from C. So that basically means that you walk along to the head of C, and rather than going from the tail to the head and attaching the tail to the head of C, in addition, which is what you would do in addition, this time we're going to attach the head of B to the head of C, and that will give us our subtracted point and the head of a new vector, which we'll call F. But for the moment, if we take that, essentially that is giving us a point there within the minus x, y, and z, and create the new vector. We can get rid of this duplicate, and now we have this new vector F, and if we check on the locator there, that'll give us the exact point of the head of this new vector. So it's -9, -2, and -11, and we can pull up the script editor, and we can run this. Obviously I've run B before, we can run it again, and then what I'm going to do is run both of these, and we will get the result for C. So C is -6, 4, and -1, and this new vector, which is F. So if we run that, and we can get a result. Okay, so this is from the subtraction of B from C, and the result of that is 13, 4, and 8. That is, they are the coordinates, but the exact point of the head of this new vector F, we'll have to run this code here. So then we can just run that there. So there we have -2, -9, -2, and -11, the exact same as we calculated from a visual calculator, purely visual, rather than using the mathematical formula. So, okay, so that's our first new vector, and now what we're going to do is we're going to try and subtract C from B, and let's see if we get the same result. Okay, so now we have our B and C, and if we again walk along to the head of B and get the head of C, and that'll lead us down to the tail. So that's where that is going to lead us, and this time we're going to go for GC, sorry, for the new vector called G. And so this gave us the head after the subtraction of C from B. That gives us the head for a new vector, and we can then draw this line here, and that'll give us the coordinates and the magnitude for this new vector, which we're calling G. Okay, so if we click on the locator, pull up the attribute editor, translator, and we'll get the position 8, 4, and 1, and we can pull up the script editor, and we're going to run G. Okay. Okay. So first things first, the position is 8, 4, and 1, and it's the same as in the attribute editor. Next what we can do is we can take a look at the results of both. Okay, so the result for G is -13, -4, and -8. The result for F is 13, 4, and 8. So they're inverse, essentially they're the inverse of each other, so their direction is the exact opposite of the other one. So that essentially suggests that it's not the same either way, you know, in terms of subtraction. Okay, I'm just going to show you how to find a unit vector. A unit vector is basically a vector whose with a magnitude of 1. And how we do that is we find, first of all, the normal of a vector, and in this case I'm going to use G, which I created in the vector subtraction. So first of all, we need to subtract the tail from the head of G so that we can get our coordinates for x, y, and z. So there we have 13, 4, and 8. We then get each of those coordinates multiplied by themselves, so squared, and added together for G squared. The result is 249. We then have to find the square root of that, and it is 15.779. Okay. We then can divide each of the coordinates by the magnitude of G. So first we have the x, so that'll give us the new value when the magnitude is 1. That's for x. For y, and for z. So when we make that calculation, as you can see, that's the magnitude of the vector G. We then divide each of the coordinates by the magnitude, and if we wanted to check, we can then rerun the operation, get the square root of each of those coordinates squared, and that gives us 1. And that coordinate essentially is G with a magnitude of 1, so it gives us the direction. Unit vectors are very useful when it comes to multiplication. When a vector's magnitude is a unity, it simplifies the multiplication process. In graphics applications, vectors are used to simplify orientation of surfaces, the direction of light sources, and the virtual camera. If these have a unit length, computation time is minimized. For calculating the dot product, the two vectors that I'm going to use are b and g, which we've both used before. The importance of the dot product, really, it gives us a scalar, so one number. In this case, we're going to try and find the angle between b and g. So what we need to do is, I'm going to pull up my script editor here, and we have we've done this before, but we'll go through it again. So we have G, which is head of G, tail of G, head of G minus the tail of G, and the Y, head of G minus the tail of G in the Z. So run that. Get with the new coordinates, X, Y, and Z. So they are essentially calculated from subtracting obviously X, Y, and Z from the head, or the tail from the head. So that's the result there. Then we need to get each of those components squared, and put in this little bit of code here to give us this result. So that is the magnitude, the length of G, and we'll do the same for B, so tail and the head of B. And running similar operation here for b. Finally, we can get the magnitude for b. Okay, so next we are going to multiply the x points of b and g and add that to the multiplication of the y points of b and g, and then add that to the multiplication of the z points of b and g. And that'll give us 179. So if we run that, 179. At this point then we'll multiply the magnitude of b and g and divide that by 179. Okay, so that's the result there. So we then need to put that in, so it's cosine of that, but it's going to give us the answer in radians. Alright, so then we need to convert that into degrees. So it gives us 36 rounded to the nearest degree. So 36 degrees is our scalar result, and that gives us the angle between B and G. So you can see there, it's the graphical representation for that. Alright, and that is the dot product. Thank you. Okay, now I'm going to show an example of how to calculate the cross product. These are two vectors, h and j. So if I click on j, I find that its coordinates are 4 in the x, 3 in the y, and 0 in the z. And for h, it is 4 in the x, 0 in the y, and 0 in the z. So just to make sure that that is a right-angled triangle, I run the numbers in the script editor, subtract the tail from the head, do the same for j, multiply the x coordinate by the x coordinate, y coordinate by the y coordinate, the z coordinate by the z coordinate. So each coordinate will be squared, and then I get the square root of that. So it's 4 for for h, and then I'm going to do the same for j, and that's 5. Next I will multiply the x coordinate for h by the x coordinate for j, add that to the y coordinate multiplied by for h and j, plus the z coordinate multiplied by in h multiplied by the z coordinate in j, which is 16. So now I can divide 4 multiplied by 5 by 16. That gives us 0. We get the cosine of that, which is 1.5 nada nada nada. So we then copy that, turn it into degrees, and that gives us a result of 90. So we know that that triangle is definitely a right triangle. Okay, so next what we need to do is find the cross product. Get the x coordinate of the cross product. I need to multiply the y coordinate of h by the z coordinate of j, subtract that from the z coordinate of h multiplied by the y coordinate of j.
So if I go ahead and do that, the result is 0. For the y coordinate of the cross product y coordinate, I multiply the z coordinate of h by the x coordinate of j and subtract that from the x coordinate of h multiplied by the z coordinate of j. Okay, so I'll do that. And again, the answer is 0. Finally, to get the z coordinate, I multiply the x coordinate of h by the y coordinate of j, subtract that from the y coordinate of h multiplied by the x coordinate of j. And that gives us 12. So that can be represented in Maya. So if we have a look here, that is at a 90-degree angle to these two vectors. So as you can see in the representation, it's pretty obviously at a right angle from those two vectors. And that's how to get the cross product. Cross product is another useful operation in computer graphics. It's only defined for three-dimensional space. The result of a cross product of two vectors is a vector that is perpendicular to them. This property is used for calculation of normals. The normal is often used in computer graphics to determine a surface's orientation toward a light source.
So I'm just going to give you an example of how to translate using a matrix, and this is essentially the formula that I need to use. So to get the new x, y, and z points, I can use this matrix and multiply it by the original x, y, and z points. So I can get the new. So the original points are 1, 1, 1, and I'm going to add 1 in the x, 2 in the y, 3 in the z. This row by this column, this row by this column, this row by this column, this row by this column. That'll essentially give me all my x, y, and z points. So I end up having 2, 3, and 4. So if I go into Maya, I can pull up. So there is my locator, and as you can see, it illustrates it's just at the point 1, 1, 1, 2, 3, and 4. And in terms of the cube, 1, 2, 3. As you can see, so the formula seems to work to translate using a matrix, the formula, and doing it manually in Maya, you get the same result. So this is a scaling matrix. As you can see in the x, essentially where you in the translate, you would have had 1, 1, 1, and t of x, t of y, t of z. Here you have scale of x, scale of y, and scale of z in the position of, for instance, in the last where we had 1. and in fact in this example we're going to use 1, 1, 1, 1 as coordinates again. So the origin will be 0, 0, 0, and basically we're just going to scale in the x by 2 and leave the y and the z, and you'll see that when you scale in the positive it moves in the positive x direction and the origin stays where it doesn't move essentially. Okay, so, and as you can see, if we just get this, so if we were to scale by the x by 2, you can see this moves in the x, doesn't go near the y, z remains the same, and the origin stays where it began. So that's our initial point. If we then move, let's say, instead of 1, 1, 1, it's now 2, 1, 1. Okay, and that's where the location leads us. So that's scaling using a matrix to scale, and also comparing it with applying the result of the matrix manually into Maya. This is the matrix formula for a rotation in the z-axis. I'm going to rotate by 90 degrees, so this is how the matrix would look, and it'll be multiplied to find the x, y, and z, the new x, y, and z coordinates. We'll multiply that out by the original coordinates, and we get minus 1, 1, 1. Okay, so if we go into Maya, here we are in Maya. I have a cube, and the locator gives us the points 1, 1, 1, 1. If, like our result, this was minus 1, 1, 1, that's where it would end up. If we then do a 90-degree rotation in the z-axis, as you can see, the cube is aligned with that locator. So the result in the matrix is the same as doing a 90-degree rotation in the z-axis in Maya.